What's up, calculus students? We are going to move forward. And as we move forward, we realize we kind of know everything we need to know about calculus. We have a complete understanding of calculus. We'll see how we'll have different types of questions. We can talk about approximating things differently, finding different things, but like we're kind of done. Uh, with calculus, really. So we can provide a complete understanding of calculus, and that's what we're going to do. And then we're going to handle these new types of questions called rate in, rate out questions. So in the first semester, we talked about how you start with an f, which gives you some y values. You can see how f is changing. You can see how f is changing with f's slope equation. F prime, the derivative. The derivative gives you the slopes of f, tells you how f's is changing in a y's per x at a moment in time, the instantaneous rate of change. And then we then got into the derivative of the derivative, the second derivative, will tell you how the first derivative is changing. This is your y's per x, or your y's per x squared. Great. In the second semester, we introduced the idea of like a position and how the rate of change of position, if position's like at a meter mark, the rate of change of position would be like a meter per time. And we realized that a rate of change of position is a velocity, and that physics teachers use the word velocity when it's really just the rate of change of position. And then the second derivative would be the rate of change of the first derivative, or the rate of change of velocity. This would be meters per second, or meters per second squared. We realize that's the acceleration, which is a fancy math word, fancy physics word for the rate of change of the rate of change of position. Cool. So that was the first semester. Then we talked about how uh, the sign of a derivative will tell you if an original function is increasing and how quickly it's increasing or decreasing. Cool. Then we were able to do like a sign analysis of f prime to tell us what f looked like, and then we could tell a second derivative analysis could tell us about the first derivative increasing or decreasing, which actually tells us about the curvature of a function. Then in the second semester, we started going backwards. We were able to say, if I gave you a derivative, could you give me a position? We introduced the concept of an integral. And if you're able to take the antiderivative, you're able to find a position function. Whether or not you're finding C or not, you can still use it to find information. And that's like cool. And that was like easy to understand. But really, what was new was the concept of if you accumulate it. Now, accumulating would be like summing up in like your calculator, not necessarily taking an antiderivative, but just sum up your meters per second over seconds. And all of a sudden, we realized that you got a meters displaced. And we brought in a new level to things, which is like if you accumulate your derivative, you'll figure out how much your function is going up or how much your function is going down. And this would be the same thing if you accumulated your second derivative, you figure out how much the first derivative was changing. And that's the key to this lesson. And obviously, we talked about how if you went backwards from f, you would get big F, and that would be like y times x's. And if you wanted to like accumulate F for finding the area under F, you could actually go backwards and use big F and realize that, and this is like the other key, is the way that these three things work together. Like, let's say your derivative was positive, you know your function's increasing. Let's say you know a value at A is 4. Let's say with your calculator, you found that this number was 5. Well, you'd be able to find that B is 9. But conversely, let's say you weren't able to use a calculator. Let's say you wanted to accumulate something. You could look at its antiderivative, whether it's with a C or without a C, and you realize that these two numbers should be subtracted, and you would be able to get this value here. Okay, so that was important, and that's how we kind of accumulated F If you accumulate F, you need big F for big P. And that's calculus, guys. Like going forwards, going backwards, accumulating to get displacement, or taking the antiderivative to get the position function. There you go. Today, here's our situation. We have these rate in, rate out questions. What you're going to realize, it's very much like Unit 7 with a calculator. So let's make sure we understand what's going on. And then we'll kind of analyze it and then realize the situation. So we got the rate at which rainwater flows into the drain pipe is modeled by the function R, as capital R. R of t is 20 sine t squared over 35 cubic feet per hour. I'm going to go ahead and highlight the fact that it's called a rate, and this is in cubic feet per hour. The pipe is partially blocked, allowing water to drain at the other end of the model D. I'm going to go ahead and highlight that this is also a rate, and this is also in cubic feet per hour. There are 30 cubic feet of water in the pipe at time 0. Okay, what is going on? Well, here's the situation. We have some sort of pipe, but there's two factors that are at play. And we are going to analyze like some sort of position, this water level. Okay, and is the water level increasing or decreasing? When is this going to be the max water level, min water level, et cetera, et cetera? And we realize that what's happening with this pipe is that there's water flowing in and there's water coming out all at the same time. Okay, so water's coming in and water's going out. We're told that R is going to be telling us something about the water flowing in, and that D is telling us about the water that's flowing out. But you got to understand, where do R and D fall on our chart? Is it a position? Is it a derivative of position? Velocity? Is it an acceleration? And I'm going to give like the motion units to help you. Okay, so motion in Unit 7, we had like meters, we had meters per second, we had meters per second squared. Well, let's read the question carefully. The rate at which rainwater flows into the drain pipe. Cubic feet per hour. The rate flows out of the drain pipe. Cubic feet per hour. What we realize is that R and D are both velocities. They are both rates of change, a y's per x, a meters per second, in this case, a cubic feet per hour. We're also given a position, like my amount of water at time 0 was 30. That's cubic feet. That's a position. So we were given one position, we were given two velocities. What we'll need to understand is that if you want to find how much total water that has come in or how much total water that has gone out, we're going to have to either take the antiderivative. Well, I can't take the antiderivative of that. So instead of anti-deriving, we could accumulate. We can use our calculator. We can find the cubic feet per hour, or times hours, cubic feet per hour times hours to get cubic feet. So we are going to use this idea of accumulating your velocity, but now it's velocities to get a total. And let's see how that plays out, and we'll realize, an extra little thing that will help us understand this idea of two things happening at once. The question is, how can you find the total amount of water in the pipe at time 8? Well, I want my position at time 8. Well, I have my starting position. This is the idea of, hey, the derivative is going to tell me how the position is changing. If I accumulate the derivative, I'll be able to figure out how much my position changes from 0 to 8. Well, I have a position at time 0. My position at time 0 is 30. I want to find out how much my position increases or decreases. Well, for right now, we realize that there's two things going on. We will be adding water coming in, and I'm going to have to add the accumulation of R because R is a rate in. If you accumulate a rate, you'll get a total. If you go backwards from a velocity, you'll get a position. And we have water going out. Well, it makes sense that I should subtract the water going out. Cool, and I can type this into my calculator, but I'm going to show you a different way to handle things. Because watch what happens when I look at the derivative of my position. Well, this is just a number. The derivative is just 0. If I have the derivative of this integral, or if I'm talking about my velocities that are going into the rates of change that are going into the position, I realize that I have R by itself, and I'll have D by itself. All of a sudden, I have this equation of the velocity of the water in the pipe. Now, this is different. Last unit, you were used to just being given the velocity. You're like, hey, this is the velocity. And you're like, cool, let me just like graph the velocity. Well, now since there's like two different rates of change going in at once, we have to subtract them. And now we have like this idea of my velocity is my rate in minus our rate out. Cool? Which means if we wanted to use the idea of the derivative telling me how much my position is increasing, and if we want to accumulate our derivative, we could change this to not two separate accumulations, but one accumulation. Accumulate your velocity, or accumulate V, so long as V is R minus D. All right, and we're going to do this on our homework. That's our first homework problem, is this idea. And we're going to talk about how using Desmos makes everything very easy. You will be able to type them all in. You'll be able to subtract them separately. You'll be able to label them correctly. It's very, very nice using our friend Mr. Desmos. And I'm going to go ahead and do this problem on the homework, so I'm not going to do it here. But this is kind of the idea. And then I'll start with the different problems. Is what happens if our rates are changing for certain time intervals. Okay, so how can you find when the water of the pipe is increasing or decreasing? The maximum water of the pipe. I will look at the derivative of my position, where the position of the water is P, and then P prime is how the water is changing. And I'm going to look at my rate in minus my rate out, whatever it might be. I will figure out when this has a 0. I will make sure I understand when things are positive or negative with my derivative. That'll tell me how much my position is increasing or decreasing, and I will accumulate my derivative to figure out how much I'm increasing, how much I'm decreasing, so I can find my potential candidates, and then I'll be able to compare my candidates, find the max or min. Okay, so it's not really new again, it's just two things going on at once rather than just one thing. Really quickly, just make sure when you're reading questions, you're reading them carefully. Is the rate that the water in the pipe is changing increasing or decreasing? By how much? Remember, if you're asked if a rate is increasing or decreasing, you'll need to look at the second derivative, acceleration. So P double prime. Here I have P prime is R minus D because R and D are already derivatives. which means if I want to figure out how P prime is changing, I'll look at the derivative of P prime or the derivative of V, get that number, and that number will tell me if my rate is increasing or decreasing. Okay. One thing that is new is you're going to see these domain restrictions. And now I'm going to show you how to do this problem exactly, because this problem doesn't show up exactly on your homework, but it's a good problem. So it's the same situation where we have this water in a tank. We're going to analyze the position of the water, how many gallons are in the tank. We're going to see their water comes in and their water is going to be going out. However, you can see the rate in F is consistent from 0 to 7. We're going to be using this. But the rate out, G, changes. We have two different G's. I have this like rate out from 0 to 3. I'll call it G1. And I have this rate out from 3 to 7. I'll call it G2. Now I know that the derivative of my position will be my rate in gallons per hour minus my rate out in gallons per hour. However, you can list this as your velocity, V in minus V out. However, what we're going to realize is that we need two different velocities. We're going to have a velocity from one interval, which will be F minus G1. And this is going to be from the interval from 0 to 3. And then my velocity 2 will be F minus G2. And that is going to be used from 3 to 7. And as we do the homework problems, you'll see how this is happening. And I'm going to show you this question because it's a great question. We can graph my rate in exactly how you see it. And we're going to start using domain restrictions. Now watch this. Add your funky parentheses. I do shift and bracket, my funky brackets. You can literally type in 0 less than equals. So press the less than shift comma, and then shift plus, add the equals, t, less than equal to 7. What's great about this is that you'll only be graphing f over the interval in which it's going to be occurring. You're going to see this time around we're going to probably be adjusting our y and our x-axis a little bit more. Whether we are just adding a bunch of zeros to our y-axis, that way we can see things. And there you go. That is the rate at which water is flowing in. We can also adjust our x-axis. We know we're going from 1 to 7, so might as well go from -1 or from 0 to 7. Might as well go from -1 to 8. Again, I'm hitting this graph settings to adjust my y-axis, my x-axis. Cool. Now I have G1. Now look, I just typed in G, then I clicked on 1, and it immediately goes to G1. And G1 is 250T, but it's only over the interval 0 to 3. Cool. You can see G1 is right there. Perfect. I'll set G2. 2000 plus 600 sine t squared over 100, and that's going to be from 3 to 7. Funky brackets, 3, 7. Great. Now, I actually don't want to look at all three of these things at once because I want to look at my velocities, both of them playing with each other at the same time. So I'm going to say that my first velocity is f of t minus g1 of t. Boom. It graphs it perfectly over the interval in which we're using it. It stops at 3 because g1 is being used until 3. And then my second velocity is going to be f of t minus g2. And that's going to pick up at 3 and go to 7. And now I can hide my first 3 because I don't want to look at them and realize, oh, look. And I am going to look at the first 2 and the next 2 just to prove a point. This is p prime. This is my derivative of the amount of water in the tank. This is my velocity. This is my gallons per hour, whatever. We can see we have this 0 here at 2.5. You can see that my derivative is negative, and then it's a 0 that is positive. Well, let's look at them separately. Here, this is my rate out. G1 is how quickly things are going out. My rate out is bigger than my rate in. That's F. That's the red line. My rate out is bigger than rate in. More water's flowing out than flowing in at these moments. You can see that my derivative should be negative. I should have these negative velocity values because my water level is decreasing. Boom, I have it. You can see when is the rate out equal to the rate in? Well, that's when my derivative is going to be 0. If rate in equals rate out, subtract the 2, your velocity is 0. Your velocity 0 means like you've stopped rising or falling. You're about to change directions. And boom, then we switch over to my rate in being bigger than the rate out. Here is my derivative being positive. What's interesting about this is it becomes this piecewise deal where all of a sudden we have negative derivatives of 0, positive, and then immediately jump from this positive to a negative. Which means if I were to look at the derivative in a sign analysis way, I would start at 0. Okay, cool. I can see my derivative is negative until this 2.5 value. I'll just call it A. Probably going to save that A. And then it's positive until 3. And then all of a sudden at 3, it immediately shifts to being negative. And that's kind of new. Like we're not crossing 0. We have this undefined derivative value, but we are going to have like a max there. And then we have this negative derivative until B, and we have a positive derivative to finish it up. Okay, now we can see like where our potential candidates are for our mins or our maxes. We'll have a potential max at 0, and I'll increase. I have a potential max at 3. Then I'll decrease and I'll have a potential max at 7. So these are the ideas that we've used last unit, and we're using again only with multiple velocities kind of interacting with each other. All right. So if I wanted the total amount of water times 7, I would do my initial amount of water I would accumulate my velocity over the 0 to 7 seconds. However, in reality, what I have to do is accumulate V1 from 0 to 3 and accumulate V2 from 3 to 7. Or you could have kept everything separate. I prefer this. I like this. Just kind of like plays into what I know. I could have said I have my 5,000. I have all of my water flowing in, and then I have my 2 separate waters flowing out. I'll subtract 0 to 3, G1. I'll subtract 3 to 7, G2. If you type this in or type this in, you're going to get the same exact thing. You're just going to have to make sure when you're doing your Desmos that you label V1, V2. Make sure you integrate the correct thing. Let's say we got 0, 3. V1 of T, easy to type in, easy to do. We can see from 0 to 3, I lose 248 gallons. And then from 3 to 7, I'm accumulating V2. Let's see if I'm gaining water. No, I lose a lot of water. So I lose water, gain a little bit of water. I lose a lot more water, gain a little bit of water. So overall, I'm losing a lot of water over the situation, even though it's not linear. It's not like just losing. you're going to lose water, gain a little bit of water. Like you can see if I go from 3, I guess 2.5 to 3, whatever this A value is to 3, you can see I gain a little bit of water there because my derivative was positive. Okay, so that's the idea. Is the water in the tank, when is the total amount of water in the tank decreasing? We can look. The water in the tank is decreasing from 0 to A and 3 to B. At time 2, I can see that the derivative is negative. Okay, that means my velocity is negative. That means my water is decreasing. It's very important to realize, like, P prime of 2 negative 104.893 would be in gallons per hour. You got to realize where you are in your chart. F and G are both derivatives. They're both in gallons per hour. If you integrate it, if you accumulate it, you'll get gallons. If you take the derivative, you'll get gallons per hour. So this is telling me how the position is changing. You'd say the water level is decreasing by 104.893 gallons per hour. There's your Y's per X, gallons per hour. And then if I asked you a question about is the rate of change increasing or decreasing, P double prime of 2, which I'll say is V1 prime of 2, which you can do very easily. V1 prime of 2 is 167. So you can see that this velocity is increasing. It's increasing 167.16 gallons per hour, gallons per hour squared. You would say that since this is positive, that the rate of change is increasing. Okay, let's go ahead and figure out the max min question, and then that's it. I'm going to skip the no calculator question, which is on the next page. We don't have the time to kind of go into it and do it. We will come back to it. So we have P prime. Let's find the A value. Let's find the B value. Okay. So what do we want? The max and the min. Why don't we do the min? All right, well, T equals A, because my water level decreases, then increases, then decreases, then increases. My candidates are actually just at A and at B. Because I go down, then up, then I go down, then up. So T equals A and T equals B are candidates. And I would write down the numbers, but I'm not going to do that. T equals A and T equals B are our possible mins, because P prime is negative from 0 to A, from 3 to B. P prime is positive from A to 3 and from B to 7. That shows me what my possible values are. Now I'm going to find P of A by taking my 5,000 gallons that I started with, or is it 3,000 gallons? 5,000 gallons. Don't forget these extra values. Adding my accumulation from 0 to A of V1. I'm going to make sure I wrote down that V1 equals F minus G1. And then I'll find P of B, which is either you can go off of A or you can just start from the start. My 5,000 plus my accumulation from 0 to 3 of V1 plus my accumulation from 3 to B of V2. Because V2 is different than V1, I can't accumulate over your entire interval. So I'm going to do that. All right. So let's just do it up here. 5,000 plus 0 to A. Oh, this is A. This is B. Of course, it's undefined because I was trying to accumulate V1 to 5.56. I can't accumulate V1 from 5.56 because G1 only exists from 0 to 3. So there's 4718 gallons, point whatever. And then P of B is 5,000 plus this from 0 to 3. I have to accumulate all of my velocity from 0 to 3. And then I have 3 to B. 3,400. This one kind of makes sense based on looking at the graphs. This is going to be my winner. This is going to be my min. Why? Because I can see like the area under my velocity, which shows me the displacement, shows me there's a lot of volume decreasing. My position is decreasing a lot from 3 to B, not because of the interval, but because of the area. So there you go. Review question was the average rate that the water entered. Don't forget that when you add up all of something and divide it over your interval, you will be able to get an average of that something. This is going to give me the average rate that water entered. And that's that. Okay. I hope you kind of picked up on what I put down here. We're going to do a lot of the problems on our homework. You will have a quiz. We're not going to do the no calculator problems, though. You would be able to take the antiderivative, find C, and subtract the values, but we're going to just stick with those, okay? So that's a good introduction. You have to do the problems. You have to use Desmos. You have to practice. So good luck out there. I'll see you on the homework video.